This lecture discusses how to construct confidence intervals for one population mean when the population standard deviation sigma is known. Some notations first. When we discuss a general formula for confidence intervals, the confidence level is usually expressed as 100 1 minus alpha percent. Here, alpha is a number between 0 and 1. For example, for a 90% confidence interval, alpha equals 0.1. For a 95% confidence interval, alpha equals 0.05. For a 99% confidence interval, alpha equals 0.01. We have discussed the notation Z alpha before. This quantity is also called the upper tail percentile. It means that the area to the right of this number is alpha. For example, the area to the right of Z 0.05 is 0.05. The area to the right of Z alpha over 2 is alpha over 2. To find the exact value of the alpha, we need to use the standard normal table. Assume X is normal with mean mu and a standard deviation sigma. The sample mean X bar is also a normal distribution. The mean is mu and its standard deviation is sigma over square root n. How to construct a 100 1 minus alpha percent confidence interval? We just need to find 2 points such that the area between these 2 points is 1 minus alpha. The area to the left is alpha over 2, and the area to the right is also alpha over 2. Because the mean of X bar is mu, this interval will contain mu with probability 0.95. We have discussed before how to find such a X value from a probability. In terms of a standard normal curve, the 2 points are negative Z alpha over 2 and Z alpha over 2. We can calculate the corresponding X value from these Z-scores. Therefore, the 100 1 minus alpha percent confidence interval for the population mean mu is X bar minus Z alpha over 2 times sigma over square root n. X bar plus Z alpha over 2 times sigma over square root n. This slide summarizes the assumptions and steps to find confidence interval for mean. Such confidence intervals are called Z-intervals. The assumptions include simple random sample, normal distribution, and sigma is known. Simple random sample makes sure that the observations are independent of each other and follow the same distribution. The population distribution should be normal. However, if the sample size is large enough, the normality assumption can be dropped. Recall that we mainly use the property of X bar in the construction of confidence interval. When the sample size is large enough, due to the central limit theorem, X bar approximately follows a normal distribution no matter what the population distribution is. The third assumption is that the population standard deviation is known. This assumption may not be realistic because it is unknown in many practical applications. We will discuss the scenario with an unknown sigma later. Right now, we assume that sigma is known. Follow the steps below to construct a 100 1 minus alpha percent confidence interval for mu. First, we need to identify the number alpha and then use the standard normal table to find Z alpha over 2. Next, calculate X bar, the sample mean, from data. The confidence interval for mu is therefore X bar plus minus Z alpha over 2 times sigma over square root n. Last, make sure to interpret the confidence interval. Notice that when the population distribution is normal, this confidence interval is exact. Otherwise, the confidence interval is approximately correct only when the sample size is large enough. In this slide, you can find the value of alpha and z alpha over 2 for some common confidence levels. You should check this table to make sure that you know how to find these values of alpha. The value of z alpha over 2 is found using standard normal table. You can also find it using Excel. Let's check in more details when we can use the one mean z interval procedure. We discuss different scenarios according to different sample sizes. For small samples of size less than 15, the z-interval procedure should be used only when the variable under consideration is normally distributed or very close to being so. In this case, the central limit theorem does not apply. If the population is not normal, X bar cannot be approximately by a normal distribution. Therefore, the assumption for the z-interval procedure does not hold. For samples of moderate size, here we mean that the sample size is somewhere between 15 and 30. The z-interval procedure can be used unless the data contain outliers or the variable under consideration is far from being normally distributed. In this case, although the central limit theorem does not apply, the experience tells us that the z-interval procedure is applicable as long as the population distribution only slightly deviates from normality. Here we want to point out the influence of outliers. Notice that the sample mean is not robust to outliers. The existence of outliers may change the sample mean dramatically. Therefore, we should not use the z-interval procedure if there exist outliers when the sample size is moderate. For large samples of size larger than 30, the z-interval procedure can be used essentially without restriction. In this case, even if the population distribution is not normal, the central limit theorem kicks in and X bar approximately follows a normal distribution. Here we want to discuss more about outliers. We just mentioned that X bar is not robust to outliers. Therefore, confidence intervals are not robust to outliers either. When there exist outliers, we may first want to check whether it is reasonable to remove outliers. A common reason for outliers is recording error. For example, you misplaced the decimal point. Such outliers should be removed from your data. It is also possible that outliers are legitimate. If outliers are present and their removal is not justified, you should compare the confidence interval obtained with and without the outliers to see what effect the outlier has. It means that we will construct two confidence intervals, one with the whole original data and one with outliers removed. We need to compare these two confidence intervals to see whether they are similar or quite different. If these two confidence intervals are substantially different, use a different procedure or take another sample if possible. The procedures that are robust outliers. The procedures that are robust to outliers usually belong to non-parametric method. They are beyond the scope of this course. We just need to know that there exist some alternatives to what we are discussing now. You will learn them later in other advanced statistical courses. If outliers are present, but their removal is justified, particularly after removal, the remaining data satisfy the assumptions for the interval procedure. You can apply this procedure to the data with outlier removed. Here, I want to emphasize a fundamental principle of data analysis. Every statistic procedure we are discussing in this course requires some assumptions. Before performing a statistical inference procedure, examine the sample data. Check whether the assumptions are satisfied or not. If any of the conditions required for using the procedure appear to be violated, do not apply the procedure. Instead, use a different, more appropriate procedure. For the z-interval procedure, the most important assumption is the normality assumption. Recall that we can check the normality assumption using normal probability plots. Let's look at one example. The data contains the age of 50 people randomly selected in the civilian labor force. Find a 95% confidence interval for the mean age, mu, of all people in the civilian labor force. Assume that the population standard deviation of the age is 12.1 years. This problem asks for a confidence interval for the population mean. The sample is a simple random sample. The population standard deviation is given. To check the normality assumption, we need to draw a normal probability plot. However, because the sample size is 50, the sample size is large enough. The central limit theorem is applicable. In this case, we only need to worry about the outliers. The box plot shows that there is no outlier. Recall that an outlier is an observation that is smaller than first quartile minus 1.5 times interquartile range, or larger than third quartile plus 1.5 times interquartile range. In a box plot, outliers are represented by dots beyond the lower vertical line and the upper vertical line. Here, no point is beyond these two lines and therefore no outlier. Let's construct the confidence interval following the steps. First, find the alpha over 2. Because we want a 95% confidence interval, alpha equals 0.05. The alpha over 2 equals the 0.025. Its value is 1.96. The sample size is n equals 50. We can calculate the sample mean. X bar is the sum of the numbers divided by 50. Its value is 41.4. Therefore, the 95% confidence interval for the mean is X bar plus minus the alpha over 2 times sigma over square root n. We have identified these values. Just plug in all these values. The 95% confidence interval for the mean age is 30 to 44.8. When we choose plus in the formula, we get 44.8, the upper end of this interval. When choosing minus in the formula, we get 38, the lower end of this interval. We can be 95% confident that the mean age, mu, of all people in the civilian labor force is somewhere between 38 years and 44.8 years. Recall that the confidence interval are usually in the form of point estimate plus minus margin of error. For the confidence interval for mean, the margin of error, denoted by E, is z alpha over 2 times sigma over square root n. This diagram is informative. The confidence interval is centered at x bar, the sample mean. The margin of error is exactly the distance between the center and one end of the interval. The total length of the confidence interval is twice the margin of error. The margin of error indicates the accuracy of the confidence interval. Usually, a confidence interval with a small margin of error is more favorable. We can see that the margin of error depends on three quantities: the standard deviation, the sample size, and the value of alpha. For a given problem, the standard deviation is fixed. Therefore, we can adjust the sample size and the value of alpha to achieve a different margin of error. For the example of age of the civilian labor force, we have already constructed a 95% confidence interval. Now, let us construct a 90% confidence interval. We want to demonstrate the relationship between confidence level and accuracy. For a 90% confidence interval, alpha equals 0.1. Then, z alpha over 2 equals z 0.05 equals 1.645. Therefore, the 90% confidence interval is 38.6 to 44.2. The diagram draws two confidence intervals together. We can see that both confidence intervals are centered at 41.4, which is the sample mean. The 90% confidence interval is shorter, while the 95% confidence interval is wider. For fixed sample size, decreasing the confidence interval decreases the margin of error, and hence improves the accuracy of a confidence interval estimate. This statement is expected because the shorter a confidence interval, the less chance it contains the population mean mu. This example illustrates the relationship between sample size and accuracy. Draw another sample of size 200. The sample mean is 42.2. Notice that this sample mean is different from the sample mean of the sample size of 50. Following the same steps, we can construct a 95% confidence interval based on this sample of size 200. The confidence interval is 40.5 to 43.9. Clearly, the confidence interval based on the sample of size 200 is much shorter than the confidence interval based on the sample of size 50. For a fixed confidence level, increasing the sample size decreases the margin of error, and hence improves the accuracy of a confidence interval estimate. It is consistent with our heuristics. The larger the sample size, the more accuracy confidence intervals. Sometimes we may need to determine the sample size needed to achieve a given accuracy. The sample size required for a 1 minus alpha level confidence interval for mu with a specified margin of error is given by this formula. The needed sample size equals z alpha over 2 times sigma over e squared. The answer may be a decimal. We need to round it up to the nearest whole number. Notice that it is rounding up, not rounding. For 99.9, so we round it up to 100. For 99.1, we also round it up to 100. This formula is obtained by the relationship between margin of error and the sample size. The margin of error equals z alpha over 2 times sigma over square root n. Do a little bit algebra and we will get square root n equals z alpha over 2 times sigma divided by e. Both sides square, and we get the formula to calculate the sample size. Let's check one example. Determine the sample size needed in order to be 95% confident that mu is within 0.5 year of the point estimate x bar. In this problem, the confidence level is 95%, or alpha equals 0.05. The margin of error is E equals 0.5. We need to find the sample size. When alpha equals 0.05, the alpha over 2 equals the 0.025 equals 1.96. Applying the formula in the previous slide, we can calculate n equals 2249.79. The sample size is the smallest whole number larger than this one, or 2250. If 2250 people in the civilian labor force are randomly selected, we can be 95% confident that the mean age of all people in the civilian labor force is within 0.5 years of the mean age of the people in the sample.